Great. Hello, everyone. Welcome to the AVM meeting. It's a great pleasure to have Dr. Ilia Kaminker today as our speaker. And Ilia is from Tel Aviv University. He completed his PhD at the Weizmann Institute and worked with Professor Shimon Vega, Daniela Goldfarb, and Song Yihan. He is very well known for his contribution to understanding DNP mechanisms and also development of advanced hardwares. And in the recent years, he's been driving EPR to new heights and literally taking it to higher fields and even incorporating with magic angle spinning. And today he will be sharing his insights into these high field EPR implementations. Ilia, whenever you're ready, just feel free to make a start.
Yeah, okay. Thank you so much, Yuji. Thank you for the introduction, and thanks all the organizing team for the invitation. It's my pleasure to describe what we've been doing here for the past six years or so. So I'll be talking about EPR and how it's used to learn something about dynamic nuclear polarization. And mostly I will show you the instrumentation that we've built to basically tackle these problems, but I will also show you on the way some examples of how it works. Okay, so let's put this in some general framework. And in principle, I'm talking to a spectroscopy crowd, so it's not very difficult to explain you why we need high signal to noise and why we like those peaks and large signal. The problem is, and it's less severe on the EPR side, but it's much more severe on the nuclear magnetic resonance NMR side, is that oftentimes you put your sample and then you get something that looks like this. And of course, we all want our spectra to look like something on the left, because then we know what to do with it. And NMR community has developed a huge array of experiments where essentially, in some sense, you trade off signal to noise for resolution or for information or whatnot. And one of the recent approaches to deal with the low signal to noise of nuclear magnetic resonance is what's called dynamic nuclear polarization. Okay, and to explain you how it works and what DNP is about, I need to first state the problem. And the problem is that because in nuclear magnetic resonance we are talking about megahertz size interactions, the energies are so small that the Zeeman interaction has energy that is much below the KT at room temperature and practically actually at any practical experimental temperature. Therefore, there will be a lot of spins that are in spin up and a lot of spins in spin down state, and only small excess, which doesn't have a pair, will contribute to a signal. We refer to this as low polarization, which is defined as number of spins up minus number of spins down divided by the total number of spins. Of course, electron spins have 1,000 times, 660 times higher gyromagnetic ratio, and so situation is 1,000 times better in terms of polarization. For a signal to noise perspective, it actually helps that now we are dealing with photons that carry much higher energy too. But let's stay with polarization. If we somehow could transfer the polarization from nuclear spins to electron spins, from electron spins to nuclear spins, we would immediately gain huge, we'll get a huge boost in signal to noise. And that's basically what DNP is about. We'll get into the details later, but for now, let's say that we need to irradiate at electron spins, which at high fields would be with the millimeter waves, and then some magic happens that we call DNP, and we get higher nuclear polarization. It's of course, on the nuclear side, it's a metastable state, but on this metastable hyperpolarized state, we can perform experiments. And if you are able to maintain this state, or at least for long enough to be able to perform an experiment, then everything is good, and we are good, and we have our spectra. A few things that are specific to NMR. Magnetic interactions, the anisotropic part of magnetic interaction, at least to first order, behaves as 3 cosine square angle of the direction of the interaction, like direction relative to the magnetic field. And it was rather early realized that it is possible to average this anisotropic interaction by fast rotation of the sample, which is positioned at the magic angle. And magic angle is the one that nullifies this expression, and it's about 54.74 degrees. Now, this works really well in nuclear magnetic resonance in solid state. Why is it so? Because interactions are in the kilohertz range. And in order to average something, you basically need to be able to acquire signal longer than a rotation period, because you want to sample all orientations. It's pretty intuitive. And if interactions are in the hertz to kilohertz range, then rotating at several kilohertz will already be enough to average those orientations. And in nuclear magnetic resonance, there are a lot of interactions that fall into this hertz to kilohertz range. So spatial averaging really works well. The second requirement is related to the first. We need to be able to acquire a signal that is longer than the rotor period. Again, the signal needs to survive longer in order to be able to be averaged, right? So this again works really well because coherence times are in the sub-millisecond to millisecond regime, which amounts to many rotor periods if rotation speeds are in the kilohertz range. And that's where they are in kilohertz or 10 kilohertz range nowadays. And therefore, spectra become highly resolved. It also boosts the sensitivity because lines become narrow and signal, and narrow line means higher intensity. And that's basically how it looks. That's a simulated example, but realistic one. We go from a broad static spectrum to a narrow lines, high resolution, and high intensity. On the EPR side, it hardly works. And it hardly works because typical interactions are in the hundreds of kilohertz and well into the megahertz and higher range. Coherence times are small, so there is not enough time for a signal to survive over a rotor period. And there is no gain in resolution except for very special cases. And usually sensitivity actually goes down, that you can see here. That is one of the only publications. So back in the 90s, there was a short period of time where group of the SPICE group, they did some experiments with magic angle spinning EPR, but that's more or less the only sample where something came out of it. It was a malonic acid sample. Okay, back to modern times. Okay, so modern NMR is carried out with magic angle spinning, and in addition to that, long time ago, EPR and NMR were carried out at similar fields. Both used electromagnets. Since late 70s, roughly, when superconducting magnets were introduced, NMR moved at higher and higher and higher magnetic field, and modern spectrometers operate above 7 Tesla, or you would say above 9.4 Tesla, even nowadays, 400 megahertz. And in solid state with magic angle spinning. What makes studying DNP difficult as the DNP experiments are done where NMR experiments are done. And there is very good reason for that, because we want to maintain the resolution. Okay, the reason why NMR went to higher and higher fields is because there is a gain in resolution. Also in sensitivity, but resolution is really crucial. You spread out chemical shifts and spectra become more resolved. Therefore, for NMR, high fields and magic angle spinning. EPR, as you well know, is mostly done at very low fields compared to NMR. X-band at 0.3, Q-band at 1.5 Tesla. And of course, we always do it as a static experiment. So the challenge at looking at the electrons under DNP conditions is that DNP conditions is basically magic angle spinning at high fields, while EPR is somewhere down there in terms of magnetic field, and the highest field EPR spectrometer is more or less where the lowest field DNP spectrometer is, at least in those that you can buy from Bruker. And just to maybe highlight that this looking at electron spins under DNP is important, I think at least 2 out of, I think it's about 4 of those installed in the world. I mean, high field EPR spectrometer at 9.4 Tesla, maybe a bit more. but at least two of them, and Benatti group and then Brisner group, were very heavily invested in looking at DNP. So there's a lot to learn there from EPR experiments, but it's very hard to get there. So when I started my group at Tel Aviv University, yeah, and of course, I haven't said that, no mechanical spinning whatsoever on the EPR side. So when I started my group in Tel Aviv University, I was looking what is the highest field that you can realistically build an EPR spectrometer. 14 Teslas sounded about right. So we did this. That was the goal of the project. And for technical reasons, it's rather easy to operate at exactly half of the field and half frequency. So our spectrometer can work either at 14 or at 7 Tesla, and I'll show you the details in a bit. So that was the project goals as I set them for my laboratory at Tel Aviv University. We were building a 388 gigahertz, so 13.8 Tesla spectrometer with pulse CW and electron double resonance capabilities. NMR because we wanted to record DNP, and if you have EPR plus NMR, you practically have DNP for free. Not really, but let's say it's so. And operation between 10 and 300 Kelvin. Again, that's about where DNP research is done. That's how my laboratory looked after about 5 years, about a year ago. And the main thing in the middle that you see is a magnet, and it's a very, very crucial part of equipment in my lab. It's a very nice magnet by Cryogenic, a UK company. It's a 14.1 Tesla magnet, 600 megahertz, cryogen-free, actively shielded. And it's a combined magnet in a sense that it is suitable for both EPR and NMR, at least solid-state NMR experiment. It has pretty high homogeneity if you want so. It has 8 shim coils. If they're energized, we can get to about 1 ppm line width. And that's for a sphere of 1 centimeter. Real samples are smaller, so homogeneity is even better than that. In addition, it has a sweep coil, which allows us to record field sweep EPR spectra. And perhaps the third thing that I should say that it is also possible rather easily to move the main field. So power supplies can be easily reconnected to the magnet and the main field can be changed, also for experiments. It takes about 5 days to cool it down and then about 1.5 days to charge. It's much faster to 7 Tesla, but it becomes slower charging becomes slower between 7 Tesla and 14 Tesla because you get closer and closer to the critical temperature for the superconductor. Okay, so we have a magnet. What next? And what next? We need a frequency source, right? Nuclear Zeeman is linear. The energy that we need to hit the transitions is linear with field. At such high field, it's no longer a microwave. The slide is stolen from the ETH website, but it becomes a millimeter wave. Okay, and millimeter wave pose their own problems because the solutions that work well for microwave stop working for millimeter waves. In particular, all components and single mode waveguide pieces become extremely lossy to the extent that about 200 gigahertz, many waveguide based components such as circulators, isolators, and so on just don't exist anymore. Second challenge is to find a frequency source. And in principle, at least in the magnetic resonance community, there are 2 of those. Okay? One of them is gyrotrons. They're extensively used in dynamic nuclear polarization experiments. They have narrow bandwidths, and by bandwidths I mean tuning range. They're not flexible in the sense that basically turn on, turn off device, no frequency adjustment, no power adjustment, at least not easily. Phase stability is poor, at least on the EPR side, and price is very, very high. On the other side of this range, the advantage is very high power that you can get out of those devices. On the other side lie solid state sources. They have low power large bandwidth. They can be tuned over wide frequency range. They're flexible. They can be pulsed. Phase stability is high. Price doesn't become low on those. Don't think so, but they're more affordable. We went with the second part because basically we wanted to do EPR, wanted to do advanced EPR experiments, and phase stability and flexibility are crucial for that. That's what we got from Virginia diodes. About half a watt power at the 7 Tesla range, so 190 to 196 gigahertz, and about 100 milliwatts in the high frequency range, 14 Tesla, 380, 392. Compare it to about kilowatts or hundreds of watts that you have at X band and Q band. So we are dealing here with much lower powers. So the design of the instrument in part takes care of that, because we are very careful about what we are doing with this very precious millimeter waves. In order to understand, few next slides, I just wanted a brief reminder about spin physics. And spins absorb and emit, they basically interact with circularly polarized radiation, which of course can be thought of as sum of two linearly polarized fields, and the other way around. If we have a linearly polarized field, for example, we excite our spins with linearly polarized fields, we can think about it as a sum of two oppositely oriented circularly polarized fields, where one of them, this one, will interact with the spins, and the other one will be just ignored. So how do you build a spectrometer? So as I told you, we start with a solid-state source. Solid-state source basically has two components. It has a synthesizer, which provides a base frequency, and then amplifier multiplier unit, which is a series of amplifiers and doublers or triplers, frequency doublers, frequency triplers. And this one gives a frequency multiplication of 12. So we get from about 16 gigahertz base frequency to about 190, 196. Then there is a second doubler, which brings us to 380 gigahertz, and that's a resonance frequency for about 14 Tesla. Okay, we have phase shifters, attenuators, and then after we are at the high frequency, essentially we are working quasi-optically. Again, no waveguide-based components, so bridge becomes quasi-optical bridge. And let's see very briefly how it works. So amplifier multiplier chain connected to a transmitter horn. So then our millimeter waves travel in free space through various quasi-optical components. And what happens there is that our linearly polarized beam goes through a wire grid, passes freely through it, goes through a Faraday rotator, rotates, another wire grid, and then it hits a mirror. That's a 45-degree mirror, which basically will now guide the millimeter waves towards you. The bridge in our design is positioned below the magnet. So here is our magnet, and we are looking into the bore from the top of it. Okay. Now I'm flipping the same illustration to the side. Our millimeter waves now come from the table up here through the waveguide and into the taper. They are focused by the taper and get into the probe. Here is the zoom into it. So taper, sample holder made of Teflon, and then they get to the sample. There is a mirror up here, and then signal goes back. So excitation beam hits the sample, and then signal goes down through the taper back onto the quasi-optics table. As I told you, the signal now is circularly polarized. That's what spins know how to do. It's split into two into this wire grid. Half of it gets into the signal. The other half is dumped into this absorber, but also the reflected power. That's what allows us to isolate signal from reflected power and not burn our sensitive detector. Detector is a mixer. And so if it's a mixer, we need to provide a local oscillator to it. And then we need to create a reference arm to have it phase synchronous, and then lock in amplifier. And after you build all this, you try to operate it, and you put a standard sample, BDPA radical, standard EPR sample, and that's what you get. You become very happy. It takes you some time to explain to your student why. And then because that thing here is a signal, you on that specific day, that was actually the first recorded signal. We worked a little bit, and it becomes like this. You worked on various small things for about a couple of months more, and then you get this spectrum, at which point you are happy because, yeah, it's practically noiseless at this point. So that's where we are. The whole probe sits in a cryostat, so temperature can be adjusted. And in this design, only sample stick goes out and then back with a warm sample. Probe stays cold, so sample exchange is rather fast, pretty similar to the design of the X-band and Q-band Bruker spectrometers, pulse spectrometers. And here probably is, I need to mention that this probe design was done together with Torsten Mahler from Bridge 12, and they also did help with the quasi-optics, and they also made the quasi-optics. Okay, so that's a graph of temperature stabilization in this cryostat. So we replace the probe at 10 minutes, and about 15 minutes, 20 minutes later, we are good to go again. So it's pretty quick. Nitroxide spectrum recorded at 100 Kelvin, again, pretty noiseless, and that's about the concentrations we're interested in for dynamic nuclear polarization experiments. So as far as CW EPR goes, we are pretty happy at this point. Of course, we are not happy overall. Okay, before I go to pulsed experiments, it is possible to record EPR spectra in field sweep mode. This is the usual mode. Frequency is held constant, field is swept. And it's also possible to do it in a frequency sweep. So frequency is changed, field is kept constant. What we find more and more is that frequency sweep experiments are actually extremely useful for this very high field experiments, mainly because if you want to do DNP or NMR for this sake, you need a very, very stable magnetic field. Field sweeps, even using sweep coil and even over small on EPR size, on EPR scale sweeps, really disturb the homogeneity and stability of the superconducting magnet on the NMR scales. Okay, and if you want to do the DNP or NMR experiment right after your EPR experiment, frequency sweep is much better because it doesn't disturb your magnetic field. So we ended up doing much more frequency sweeps than I thought we would. And what allows it is basically the fact that it's very easy to change the frequency of the source. Frequency of the source is changed, and then we can scan through it. Line intensities are not exactly the same between the two, and that has to do with the differences in power output versus frequency of the source and presence of standing waves in the system. But overall, it's a very, very useful experiment. Now, beyond CW-EPR, we wanted to learn more about DNP, and DNP, essentially what you want to know when you are looking at DNP experiments is how spins evolve in time, okay? And how they evolve in time, you don't learn from continuous wave EPR experiments. You want to do a pulsed EPR where you can excite at one time, then detect at the other. So we upgraded our spectrometer with a pulse forming unit. It goes in here. It's a 16 gigahertz pulse forming unit, home built. For the lack of time, I won't give you much details on that. Few more changes. You need to change lock-ins to a fast digitizer, but all the rest stays more or less the same. Second thing that we could do is to switch between operating at 14 Tesla and 7 Tesla, and I'll show you on the scheme what parts are actually changing. So going from here to here, a doubler that was here disappeared. We remove it. Horns are different because we need a different launching horns from a single mode waveguide to quasi-optics. This part changes because reference arm changes with the mixer. This AMC, low frequency AMC here, but that's about it. So by the time field has moved from 14 to 7, we can reset this setup and operate at a lower field, low frequency. And as I show you in a minute, it's actually a very useful feature. So back to pulsed experiments, we can measure relaxation now. T2 by tooth pulse echo experiment, T1 by saturation recovery experiment. And it is important to measure them at different fields because even relaxation changes. And we are talking here about diamond sample, solid one, where not much should have been happening. Of course, it wasn't the case. Last feature that I want to highlight is that our pulse forming unit also has AWG capabilities. So we can synthesize those nice chirp pulses. Shown here, these are real traces detected as a leak through to the EPR detector. And here is a place to send Boris Apple, who is a longtime collaborator on interfacing the spectrometers. And here are the experimental results. So chirp pulses, we can do adiabatic inversions, and here inversion profiles for these pulses at 7 Tesla and at 14 Tesla. Inversion intensity is less at 14 Tesla. That's expected because there is less millimeter wave power there. We could also show that the pulses are coherent, and we can generate coherent echoes out of those chirp pulses. And here, the higher the bandwidth of the pulse, the more narrow the echo is. That's how it's supposed to be. The intensity goes down, which is not supposed to be, but that has to do again with the limitations in power. We just don't have enough power to efficiently excite the bandwidth. We excite it, but the efficiency goes down. Adding a ref circuitry to the probes, here we have a carbon-13 configuration on the left and proton configuration on the right, allows us to record DNP spectra. Here's an example of nitroxide DNP spectrum recorded at 10K. And by DNP spectrum, I mean that we record NMR signal intensity while irradiating at a different frequency. So remember those millimeter waves that we had to irradiate to transfer polarization? We irradiate at certain frequency, record NMR intensity, irradiate at the next frequency, again record NMR intensity, and so on. That's how the DNP spectra are recorded. Let me briefly tell you a story about our investigation of dynamic nuclear polarization in diamonds. And it was started as just, we wanted to test our spectrometer. We heard that diamonds are easy to hyperpolarize, so we started with those. And the main player here is so-called nitrogen substitution, OP1 center, where nitrogen substitutes one of the carbon in the diamond lattice, and nitrogen has one extra electron, so it becomes a paramagnetic defect with spin 1/2 and nuclear spin of 1. Kind of similar to a nitroxide. Therefore, it's also a good model system to look at DNP at all. And also relaxations in diamond are much slower, so at room temperature it becomes similar orders of magnitude to a nitroxide at 100 Kelvin. Again, excellent. So again, we recorded the DNP sweeps at 2 different fields, 7 Tesla and 14 Tesla. And you can see that they're pretty similar. And then we recorded the EPR spectra. It's echo-detected EPR spectra recorded concurrently with the DNP. This by itself, I just want to highlight it. This is a very rare experimental capability. Most DNP spectrometers can't record EPR spectra, and the other way around. Most high-field EPR spectrometers cannot record DNP spectra. We can do it together on the same sample, and it is actually important because sample preparation matters, everything matters. Here we know that we are looking at electron spins as the same. Those that we measure, those that participate DNP are the same ones. When we did it, two things happened. We also actually realized that the high-field EPR spectrum looked differently from the low-field spectra in diamonds, which is quite surprising in the beginning. It took us some time to realize why line shapes changes. And there is actually a paper from our group that came out just a few days ago in PCCP describing this high-field EPR spectra. But back to DNP. I think I'll skip this introduction. Essentially, there are two mechanisms. One is a solid effect, and the second one is a cross effect. And the solid effect becomes less and less efficient the higher you go in field and frequency. Therefore, when we saw our efficient DNP, we were first of all surprised, and second, we thought that there should be something beyond the solid effect. And solid effect is the simplest one, where you have electron spin and the nucleus spin, and that's it. If they have dipolar coupling between them, you will have solid effect. Cross effect is a more complex mechanism, but it's a much more efficient at high field. And for that, you need 2 electron spins and 1 nucleus spin, and the coupling between the 2 electrons and coupling of one of the electrons to the nucleus. And what you will get is that if you have 2 electrons, the frequency, they should resonate at two different frequencies, and the frequency difference between the resonance frequencies should be the Larmor frequency of the relevant nucleus. If this happens, then the DNP is very efficient. So that's schematically illustrated here. You have 2 electron spins which resonate Larmor frequency apart, and then what will happen if you scan the DNP spectrum, that you will get a positive line and then a negative line, and the difference between them will be the nuclear Larmor frequency. The point is, and what is important for the next slide, you need 2 electrons that resonate at Larmor frequency apart. And when you look at the DNP efficient at the EPR spectrum of the diamond, and we first look at the sharp features, that's not going to happen, because Larmor frequency is just too small at 7 Tesla to provide efficient cross effect. And it's again, it's too large, or if you want it from between side lines and central lines, or too little bit if you want to have cross effect between leftmost and rightmost lines, but it's not working at neither 7 nor 14 Tesla, at least not efficiently. And then we had to look more carefully into the EPR spectrum. And if you do it, you actually realize that there is something in the middle here, that it doesn't go back to the baseline, okay? And same as the 14 Tesla. And Orit, my student, she did a really great work in understanding the system. And when you do this, you realize that you need to put another component, which are nitrogen, those P1 centers, which is strong dipolar coupling, and then another component, which has those that are even closer to one another, so they have also an exchange coupling. And then you can account completely for the line shape. But moreover, presence of those exchange coupled spins allows you now to have a pair, because they fill in the gap between the sharp lines. Essentially, you can see it also here. And then DNP becomes possible. And that's what we think is happening in those diamond samples. We can actually check for that. And for this, we needed an Eldor experiment. And Eldor experiment means that we need a pulse at a different frequency. So it's a pump pulse at one frequency, probe at the other. And here, basically, if we pump, and we pump here where only exchange coupled spins are, and then we probe elsewhere, then you can immediately see from the spectrum that it doesn't interact with the result lines. And that basically means that those isolated spins that provide the sharp lines and those exchange coupled spins that provide the broad background, they exist. At least some of them are close enough in the diamond lattice to have a mutual effect and to hyperpolarize. So that's one story about how understanding and detailed understanding of the EPR spectrum helped us to understand what's going on the DNP side. And in the last, I think about 10 minutes or so that I have, I'll show you. And the elephant in the room is, of course, DNP is done under magic angle spinning, and all you are showing me here are static experiments, and not me. That's how the EPR side of the DNP research works. So the longer I thought about it, the more I thought that we have to do it. So we started, and Alex Fialkov in my group, he did a really great job in designing this first generation magic angle spinning EPR setup. So we basically put samples inside the ball, and the ball is fitted into what's called a stator, and then it rotates. Okay, it rotates pneumatically, so it basically, when the gas here flows, it lifts the ball and it's also spins it. And the hole in the stator is positioned in such a way that the ball spins at magic angle or very close to it. And the final adjustment is done mechanically by tilting the hole set. And then everything else stays the same. Millimeter waves come from the bottom, interact with the sample inside this ball. Ball is made out of Teflon in our case. So it's just a bearing ball drilled through and sealed with a glue. And so we used diamond powder in the example that I'm going to show you, micro diamond powder. That's how the probe looks in reality. The cables are for monitoring the spinning speed, just optically as it's usually done. And this you can see here as radio frequency coil also. This is for recording the DNP spectrum. But we will concentrate on the EPR. And here is the static spectrum of the diamond powder. Center line is the n equals 0, n equal -1, and mi -1, mi +1. So the 3 states of the nitrogen spin. And because spins, the non-zero states are anisotropic, so we get this powder patterns on the side. And this is a frequency sweep echo detected spectrum. When we start spinning, we immediately see that the line shape changes, and the anisotropic part is affected more than the isotropic part. And it's not very difficult to understand, because if you think what happens here, we apply a pulse and then spins change the resonance frequency because the sample is spinning now, so the anisotropic parts change with time, and then we apply a second pulse. The bigger the change between those two pulses is, less signal there will be, because we won't be able to refocus. 2 pulses needs to be applied to the same spins in order to refocus them. So we see that the signal on the sidelines disappears much more quickly than the signal on the central line. And that's exactly because there is more anisotropy on the sidelines compared to the center. To convince you that this is the case, I'm showing you now for a given spinning speed, but I'm shortening the pulse sequence. So I'm making the distance between the pulses shorter. So less and less time passes between the 2 pulses. And then you can see how line shape is restored, though sample is still spinning. Signal to noise goes down, and that's because pulses are now short, so they become small flip angle pulses, but the line shape is back. We've had a lot of discussions with my good friend and colleague, Fred, whom you know well from National High Field Mag Lab, and he was simulating electron spin dynamics and spinning samples for the sake of DNP research for many, many years now. And then I approached him to ask him, Fred, can you please do also our EPR spectrum? And after some back and forth, he was able to adapt his simulations. And now we have very good agreement between our experimental results here on the left and Fred's simulations here on the right. What I'm showing you here is what I showed you on the previous slide, how the line shape changes with shortening the pulse sequence. Okay. It's a rather technical note, but if you have EPR capabilities for your DNP probe, you can measure the B1E intensity. Seems trivial for all people familiar with pulsed EPR instrumentation, but it's very non-trivial for the DNP side, because again, DNP instruments cannot do EPR. So in most setups, the value of the electron spin notation, so nu1e or b1e, whatever you want to call it, is actually not known. There is pretty significant effort trying to simulate it. And we, for the first time, were actually able to measure it experimentally, and it was about 200 kilohertz with half a watt of power in this setup. After that will be the last part of my presentation. We actually created a second generation of this magic angle spinning EPR experiments, and in this case, we adapted a semi-commercial DNP probe. We got a prototype made by Phoenix NMR. It's an NMR probe company, and they had a prototype of 1.6 millimeter DNP probe. We got it, made some changes to it, mainly in terms of the millimeter wave delivery. And this one has a standard spinning setup where sample is packed into a rotor. So its rotor is basically a long tube. which you fill with your sample. It has two cups on the side. One is shaped like a turbine, so a gas flow will spin the rotor, and it's held with air bearings, so essentially with airflow coming from all directions, which makes the rotor float, and then you have another gas stream from along the axis of the rotor, and it will spin it. And you can actually, so you don't see a rotor here, but it's positioned like this under magic angle spinning, and this hole here is the hole where the millimeter waves will come in. And if you do that, you can now measure EPR spectra, and I'm showing you the same two-pulse spectrum, but at higher frequencies, so 11 kilohertz and 23 kilohertz. Up to here, nothing conceptually new. So yes, you can do spectra at record high frequencies, but what next? And what next is actually important, because you want, for the sake of understanding DNP, you want to follow the electron spin dynamics over large time scales. And this echo sequence, it's time domain evolution, but over a couple of microseconds, maybe 4 microseconds was the longest one. That's not enough. You want to extend it. And extending it is difficult, because for a slow spinning sample, everything will go completely off resonance. But if it is slow spinning, by the time it comes back and again everything is on resonance, it will happen after a rotor period. There's nothing left because of relaxation. When sample spinning is faster, it is actually possible to make a pulse sequence, which is so-called rotor synchronized. We apply pulses after a full rotor period, and then you can keep monitoring the magnetization. I'll show you in a second how it works. So we have a stimulated echo sequence, because during this TD period, so it's 3-pulse sequence, and during the TD period between second and third pulse, relaxation is much slower because magnetization is stored along the Z. And what I'm going now, I'm measuring an echo intensity, okay? And I'm extending this TD. And you will see that when this distance between first pulse and last pulse becomes a rotor period, so last pulse is applied exactly rotor period after the first pulse, meaning that the same spins are now again on resonance. Then we'll see an echo. So that's how it works. Nothing, 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 up, there is a signal. And the signal here, it's a 30 kilohertz spinning. So again, 1/30, it's exactly where we expect it to be. Okay? Let's see the same, 15 kilohertz. First rotor period is at 70 microsecond. We can extend it to twice as long, and we'll see a second spike. So again, it's an echo intensity plotted versus the delay. Okay? And when it coincides with the rotor period, there is a signal. And third and fourth, and we can do the same for 25 kilohertz. And in this case, Sudipta, my postdoc, measured up to 10th rotor period. So what happened here? Now we can measure electron spin dynamics, the evolution of electron spin magnetization, but instead of 4 microseconds, we can measure up to 400 microseconds. So we can do it for 2 orders of magnitude longer. Now we are getting into the regime relevant for DNP. Okay, that's more or less the end of my presentation. Here is our magnet celebrating Purim last year. So what I've showed you is that we made a spectrometer that can do very high frequency, 14 Tesla, 388 gigahertz EPR in pulsed continuous wave, double resonance mode. We can do EPR under magic angle spinning. We can do NMR and DNP. And the last thing I want to send my group, here we are. It's a real pleasure to work with these people. A lot of work was done in diamond work was done by Orit here. Alex was a person behind magic angle spinning. David does all the radio frequency developments in the group, and all the rest contributed a lot too. A lot of thanks to School of Chemistry Mechanical Workshop. Without them, no home-built instrumentation would be possible. They're very good and nice. a lot of people from different companies helped put bits and pieces of the spectrometer together. And this is the funding agencies and a lot of my collaborators from different universities whom I really wanted to thank here. And thank you for your attention.
Thank you very much, Ilia. It's a huge amount of work. Very impressive.
Yeah. Thanks, EJ.
Now we're open for Q&A session. Anyone have any question, just post in the chat or unmute yourself and ask the question. I can start with the question. So I noticed in your design for the microwave part, you didn't use any up conversion. So you just used the frequency multiplier. Could you comment a bit on that?
What do you mean by up conversion? So frequency multiplier brings me from 16 gigahertz to either 190 or 382, and we are where we want.
Yes. By up conversion, I mean usually in our case in hyper, for example, we use carrier frequency, and we do all the
you mean mixing it at the higher frequency?
Yes, mix at some frequency and then do the frequency.
Okay. I got your question. Thanks. It's actually important one. It's a question whether you have an amplifier at the end of this or not, because in your hyper system, last piece of it is an amplifier, which is the EIK in your case. You can tolerate relatively low power and then amplify it. In this higher frequency designs, there are no more amplifiers in it. So actually doubling the power becomes more efficient in terms of how much power you get. So you get as much power as you can at 95, and not as you can, but as much power as won't burn your doubler, which come next. And then you put a doubler and then a second doubler, and that's the highest power output that you can get. So it's so that's the reason. Basically more power.
Okay, thank you very much. Any other questions?
I do have one on the more or less the same topic. So it's a technical. So you generate pulses at 16 gigahertz, and then you multiply everything up to the final frequency. Do you have any artifacts in the pulses, or is generated by the multiplications, or is not a problem? And also, how long are the pulses on average? Maybe you said that, but
it can be pretty low. Okay, so second question is easier. In the echo sequences, pulses, so those that are coherent, so to speak, they would be in the hundreds of nanoseconds to a couple of microsecond long. This is a typical pulse length. For the Eldor sequence, where we need to saturate, or for DNP, they can be as long as needed. So DNP sequence can be 30 seconds, like in the long seconds, tens of seconds. That's no problem. In principle, the shortest that the system will generate would be probably about 10 nanoseconds. We never use it because there's not enough power to see anything with 10 nanosecond pulses, but that's about the shortest it will do without too much distortion on the rising and falling edges. So for the first part of your question, we don't see much. Square pulses are practically perfect. Phase is also pretty well reproduced. There are some transients at the beginning of the pulse, but nothing that bothered us so far. You do lose amplitude control. So you cannot attenuate pulses at 16 gigahertz and expect them to be attenuated at high frequency. The amplification multiplication is so nonlinear that becomes hard. That's basically the main issue. You cannot do a nice worst pulse.
Yeah.
You can do a chirp pulse, but it will be constant amplitude chirp or whatever phase profile. But you cannot nicely attenuate the edges, for example.
Got it, thank you. And if I can, I have another question. So you mentioned that you do frequency sweep, echo-detected EPR. Is it right? So
Yes.
do you need a do you need a calibration for the power output at different frequencies so that your baseline is flat?
No, never was a problem.
Okay.
It does vary. Don't quote me now, probably about 10-20% across the range. Never was a problem.
Okay, good. Thank you.
It's not like order of magnitude difference, so never was a problem.
Okay.
And actually it's over the whole range. Over specific range, it's smaller, and actually when our amplifier multiplier chain got upgraded with a different amplifier, it actually was much more flat. So the one that we got, the most recent one we got from Virginia Diodes, has rather flat output actually. The first one was worse, and even then it worked pretty nicely.
Yeah, that's very good. The Spectra baseline were really fat.
So again, you
Just
see differences between sweep and frequency sweep, but you a lot of times don't care so much. If you do want accurate line shapes, then field sweep is better. I don't have, yeah, but you don't always care about exactly.
Question. I also have another question. So I noticed when you do the frequency sweep to get the spectrum, the broadest you were showing is about 12 gigahertz. Is that limited by the amplifier?
No, by
or
yes,
what is the
AMC has a range. Yes, so I never showed you something broader than nitroxide anyway, but the range is 6 gigahertz at the 7 Tesla and 12 gigahertz at the at the 14 Tesla. That's basically specifications of the MC. Yes.
Okay, great. I guess Thomas was also asking about the sidebands generated by the frequency multiplier when you go to a higher frequency, but in your case, so it will be multiplication
Doesn't
16.
seem to be a
So it will
problem.
be, yeah, it will be outside of your range. Maybe that's why you don't have this problem.
Perhaps, to be honest, I don't have spectrum analyzer for this frequency to really check. We never saw any, we for sure never saw any artifacts in the experiment.
Yeah, yes. I think it's because it's far enough from your excitation bandwidth. That's why it is good in your case.
There is, so that's another maybe an advantage of actually not mixing it at any point. So
yeah, I think so. I think it's
so at 16 gigahertz, sidebands are filtered very well because there is a bandpass filter there.
Yeah.
And then it's only multiplied.
Yep. Very nice. Alexei has a problem? Question, sorry.
I hope it works. Yeah. Can you hear me?
Yeah.
Yes.
Yeah. So great talk. Thank you very much. So I was just curious whether you thought of what could be a good application for this magic angle spinning EPR. So what would be the main area where that thing could be applied?
Main area is looking at how DNP works. I don't think, okay, there are two answers to it. The original idea came basically from kind of work we were doing for many years with Shimon and then later with Songi, basically using high field EPR to understand how DNP works. And then magic angle spinning changes everything. And a lot of it is known from theory by work of Fred and Rob Tico's group and so on. But the simulations, at some point, they have limitations, mainly because it's limit of how many spins you can simulate, exactly at least. So some effects and like spectral diffusion are never included. And we know, at least in static DNP, they play a huge role, perhaps also in the magic angle spinning. So that was the main idea, that was the main driving force of looking at it. Another area is more directly EPR-ish. If you think about it, then in high field Endor, you sometimes have cases where you do resolve interactions in the kilohertz range or in the tens of kilohertz range.
Yeah, that's right.
But that's on the Endor side. Not on the EPR side, it almost never happens. It does happen on the Endor side. In that case, if you would spin, you could actually improve resolution. And you can take away the anisotropic parts, see the isotropic parts of the inside. I can really imagine some crowded spectra where it will help. It's not an easy experiment.
You can think, for example,
conceptually it should work.
Yeah, you can think of some kind of complexes where you have some very weakly coupled nuclei in the kilohertz range, and you probably can look at them. Yeah. Yeah,
for example, Marina Benati's work where they resolve chemical shift anisotropy of fluorine, those kind of systems.
Yeah, okay, great, thanks.
Great. So do you have some plans to scale the spinning rate to the same as NMR or it will not?
It is actually, spinning rate is actually similar. The highest was 37 kilohertz now.
Okay.
That's a nice middle range as far as, I mean, as far as NMR goes. Depends on the collaborators. I don't know how to spin faster. So, but if somebody wants to collaborate with me on making fast spinning, I would do it. I'm pretty happy with the second generation probes, which spins up to 40.
Yeah.
That's enough to do. The next, if you're asking what's the next big thing experimentally, is doing this magic angle spinning EPR at low temperatures. For now, it was all temperature with diamonds. Next thing is to make it low temperature, which brings us, I mean, it's all in principle solved in the DNP community, but from in principle solved to working in our spectrometer, there is some, way to go.
Okay. Is there any other questions? If not, let us thank Ilia again for the very nice talk, and we look forward to hear updates from you again on the conferences. And thank you very much.
Yeah, thanks again for invitation. It was my pleasure, and see you all around. Bye.
Yeah. Okay. Bye.
Thank you. Bye.
See you in 2 weeks' time.